Hello students, welcome to the Jnanataranga program on CET coaching classes. The topic for today's discussion is chemical kinetics and surface chemistry. In the kinetics, we deal with something regarding rate of reaction. You know, the rate of reaction is normally expressed as change in the molar concentration of a reactant or product in a unit time. You have got average rate of reaction and instantaneous rate of reaction. Instantaneous rate of reaction refers to the change in the molar concentration of a reactant or a product in a small time interval, and it is given by minus dr by dt, or that is equal to plus dp by dt, depending on whether we are expressing the rate in terms of concentration of reactant or product. And the unit of rate of reaction is normally mole per liter per second or mole per decimeter cube per second. And the relation between rate constant and temperature normally is given by Arrhenius equation K equals A e power minus EA by RT, or the log form of that equation can be log K equals log A minus EA by 2.303 RT. And the temperature coefficient of a reaction, you know, the rate or rate constant of a reaction definitely changes with what is called temperature. Temperature coefficient of a reaction is equal to Kt plus 10 by Kt, where Kt plus 10 refers to the rate constant at temperature T plus 10 and Kt refers to the rate constant at temperature T. And the temperature coefficient of any reaction equal to Kt plus 10 by Kt, and that is equal to 2 or 3 depending on the reaction. And then when we consider the different reactions of zero order, first order and second order, you can compare the rate constants of each order reaction, and you can identify the order of a reaction based on all these units of rate constant, half-life variation, concentration and rate dependence, etc., etc. Now for a zero order reaction, the rate constant is given by K equals R naught minus R by T. For a first order reaction, it is 2.303 by T log R naught by R, and for a second order reaction it is 1 by T of 1 by R minus 1 by R naught. And the unit of K for a zero order reaction is mole per liter per second. For a first order reaction it is just per second or per minute. For a second order reaction it is liter per mole per second. When we give the value, when the value of rate constant for any reaction is given, based on the unit of rate constant, you can identify whether the reaction is zero order or a first order or a second order. That is one method of identifying the order of a reaction. And then T half, you know very well, is the time interval during which the concentration of reactant is reduced to 1/2 of its initial value. For a zero order reaction, T half is equal to R naught by 2K, and for a first order it is T half equals 0.693 by K, and for a second order it is T half equals 1 by K into R naught. And when we consider the variation of T half with initial concentration, so for all order reactions, T half is proportional to R naught to the power 1, 1 minus N, where R naught refers to initial concentration of reactant and N refers to order of reaction. And using this formula we can say that for a zero order reaction, T half is directly proportional to initial concentration. For a first order reaction, T half does not vary with R naught. For a second order reaction, T half is inversely proportional to R naught. And then the rate law equation for zero order is rate equals K R naught, and for first order K R to the power 1, for a second order rate equals K R to the power 2. So when we have the rate law expression as rate equals K R naught to the power 0 for a zero order reaction, when you change the concentration, I mean to say when you double the concentration of reactant, rate of reaction remains unchanged. If it is a first order reaction, so when the concentration of reactant is doubled, rate also doubles. For a second order reaction, when the concentration of reactant is doubled, rate increases 4 times, because rate equals K into 2 to the power 2, and because of that rate increases 4 times. Therefore, you can predict the order of a reaction either by the units of rate constant, or by the variation of T half with initial concentration, or by the variation of rate when the concentration of reactant is doubled. And then, so the as I said, the temperature coefficient of any reaction is equal to Kt plus 10 by Kt, and that is equal to 2 or 3, in the sense when the temperature of the reaction is raised by 10 degrees centigrade, the rate sometimes doubles and sometimes even triples for every 10 degrees centigrade rise in temperature. And increase in reaction rate is always given by 2 to the power n times, where n is equal to difference in temperature by 10. For example, when the temperature is increased from 20 to 80 degrees centigrade, n is equal to 80 minus 20 by 10, that is equal to 6. Obviously, the rate increases by 2 to the power 6 times, that is equal to 64 times. And apart from all these information, you should also know the important relations for different percentage completion of reactions for a first order reaction. For a first order reaction, T 75% equals to T 50%. That means to say, time required for 75% completion of a reaction is equal to twice the time required for 50% completion of reaction, and therefore T 3 by 4 is equal to 2 times T 3 half. Similarly, you can derive and show that for a first order reaction, T 87.5% is equal to 3 times T half, T 99.9% equals 10 times T half, and T 99% is equal to 2 times T 90, and T 99.9% is equal to 3 times 390%. The amount of reactant left over after n half-lives for any first order reaction is given by Rn is equal to R naught divided by 2 to the power n, or R naught into 1 by 2 to the power n. And apart from kinetics, if I have to tell you regarding surface chemistry, in the surface chemistry you should learn about catalysis, and then adsorption and colloids. You know, adsorption is a spontaneous phenomenon of accumulation of gas or liquid molecules on solid surface. So during adsorption, because of orderly arrangement of molecules on a surface, the entropy of the system decreases, enthalpy also decreases, free energy also decreases. Therefore, adsorption phenomenon is accompanied by a decrease in enthalpy, entropy and free energy. And if I have to tell you regarding the extent of adsorption of a gas on a solid surface, that is given by the Freundlich adsorption isotherm, which is x by m is equal to Kp to the power 1 by n, where x is mass of adsorbate, m is mass of adsorbent, and P is equilibrium pressure, and n is an integer. And the log form, when you take log for this equation, you get log of x by m is equal to log k into 1 by n log p. Hence, when you plot a graph of log of x by m versus log p, it gives a straight line with a slope of 1 by n, because this equation resembles y is equal to c plus mx, where m is equal to 1 by n, which represents the slope of the curve or straight line which is obtained by drawing log of x by m with log p. And you know, in the colloidal solutions, colloid is actually a heterogeneous solution which has got two phases, like a dispersed phase and dispersion medium, and the size of colloidal particles in the solution ranges from 1 to 1000 nanometers. And the important properties of colloids, if I have to list out, Tyndall effect is considered as an optical property of colloids which involves the scattering of light by the colloidal particles. Similarly, the Brownian movement is considered as a kinetic property of colloids because it involves the random or chaotic movement of particles because of collisions between colloidal particles and molecules of medium. The minimum, apart from that, the charge on the colloidal particles is necessary for a substance to be in the state of colloid. Repulsive force between the like charged colloidal particles is very much responsible for the stability of colloids, and therefore charge on the particles is considered as an electrical property of colloids. And when a colloidal solution is mixed with an electrolyte, definitely the charges on the colloidal particles are neutralized, and the colloidal solution, we say, gets destabilized or coagulated or precipitated. So, and the flocculation value or coagulation value is expressed as the minimum number of millimoles of electrolyte required to coagulate 1 liter of a colloidal sol by the addition of electrolyte. And then the protective colloid concept. The protective colloid is actually a lyophilic colloid which is added to lyophobic colloid to enhance its stability and prevent it from undergoing precipitation. Now, when a protective colloid is added to a phobic colloid which is relatively less stable, the minimum number of milligrams of dry protective colloid required to prevent the coagulation of 10 ml of gold sol by the addition of 1 ml of 10% NaCl is called gold number. Gold number is a measure of protective action of a lyophilic colloid. I mean to say, the gold number, if it is lower value, then the protective action of the colloid will be more. So with that synopsis, let me move on to a few questions from kinetics as well as the surface chemistry. And you have the question number 1. For the reaction N2 plus 3H2 arrow mark 2NH3, the rate of disappearance of hydrogen is 0.01 mole per liter per minute, and the rate of appearance of ammonia would be in mole per liter per minute will be. From this question, if I have to equate the rates of reaction, you know, for any reaction, reaction rate is equal to minus d of reactant, that is N2 by dt. Since the coefficient of N2 in the equation is 1, you have got 1 in the denominator, that means it is equal to minus dN2 by dt, and coefficient of hydrogen is 3, and therefore when we express the rate in terms of decrease in concentration of hydrogen, it would be equal to minus 1 by 3 d of H2 by dt, and the product is ammonia which has got 2 moles in the balanced equation, and therefore the rate with respect to formation of ammonia is 1 by 2 d of NH3 by dt. So, and rate of appearance of ammonia or rate with respect to ammonia is nothing but just dNH2 by dt, and by the cross multiplication you would get it as 2 by 3 of dH2 by dt, and therefore dNH3 by dt is equal to 2 by 3 of what is called the rate of disappearance of hydrogen, that is equal to plus 0.01 mole. Obviously the multiplication gives you 0.007 mole per liter per minute, and hence the correct option becomes option C. The next question, for a gaseous reaction 2x plus y arrow mark p plus q, the rate is given by kx to the power 1 and y to the power 1. If the volume of container containing the reaction mixture is suddenly reduced to 1 by 4, then with respect to the original rate, the new rate would be, if the volume of the reaction vessel is reduced to 1/4, definitely the concentration of the reactant X and Y increases 4 times. Obviously, the new rate would be rate is equal to K into 4X and then 4Y, and therefore, so when you multiply 4 to the power 1 into 4 to the power 1, the rate increases 16 times, and the correct option becomes option D. Move on to the next question. Oxalic acid is oxidized by acidified KMnO4 as per the equation which is there on the display, and the rate of this reaction increases with time. Probably this reaction you have carried out during the titration of what is called oxalic acid with KMnO4 in your laboratory. Normally, the initial reaction, as the reaction proceeds, the rate of disappearance of KMnO4 becomes faster. That is because of the formation of MnSO4 or manganese sulfate as one of the product which contains Mn2 plus. If one of the product formed in the reaction itself acts as a catalyst, then we call it as autocatalyst. Because of the formation of Mn2 plus as autocatalyst in the reaction, the rate becomes faster, so, and the rate of this reaction increases with time, and therefore the correct option becomes answer option D. And then we move on to the next question. The initial concentration of N2O5 in the following reaction is given as 1.24 into 10 to the power minus 2 mole per liter at 318 Kelvin. The concentration of N2O5 after 60 minutes was 0.20 into 10 to the power minus 2 mole per liter, and you have been asked to calculate the rate constant of the reaction at 318 Kelvin. For the first order reaction, you know the rate constant is given by 2.303 by T log R naught by R, and they say that the time is 60 minutes here. So 2.303 by 60 minutes into log of R naught, the initial concentration, which is 1.24 into 10 power minus 2, and then the concentration after 60 minutes, that is R, is equal to 0.20 into 10 power minus 2. And when you divide this, this is equal to 6.2. Therefore, K is equal to 2.303 by 60 into log of 6.2, and log of 6.2 is given as 0.7924. And when you multiply the log value with 2.303 by 60, you would get the rate constant as, so what is called 0.0304 per minute, and therefore the correct option becomes option B. So we will move on to the next question. In the reaction of 2N2O5 R 4NO2 plus O2, the rate is expressed as follows, and you have been asked to find out the relations between K1, K2 and K3. So when you look at the rate equation for the given reaction, the coefficient of reactant N2O5 is 2, and therefore rate is equal to minus 1 by 2 d of N2O5 by dt, and that is equal to 1 by 4 of d of NO2 by dt, because you have got 4 moles of NO2 in the balanced equation, and that is equal to d of O2 by dt, because you have got 1 as the coefficient of oxygen in the equation. Therefore, rate is equal to 1 by 2 of K1 into N2O5, because d of N2O5 by dt is given as K1 into N2O5, and that is equal to 1 by 4 K2 into N2O5, because d of NO2 by dt is given as K2 into N square bracket N2O5, and that is equal to K3 into N2O5, because d of O2 by dt is given as K3 into N2O5. Therefore, on dividing all this equation, entire equation by N2O5, and then when we multiply by 4, you would get it as half into 4, that is 2K1, and then into 1 by 4 into 4, that is 1K2, and then 1 into 4, that is 4K3. So therefore correct option becomes 2K1 equals K2 equals 4K3, and that is option B. And the question number 6, you have been given the variation of initial rate of formation of the product with the different concentration of P and Q in the reaction. They have given you the concentration of P and Q in experiment 1 to 4, and you have been asked to find out the rate law equation for the reaction. Now when you closely observe the concentration of P and Q in from experiment 1 to 4, when you consider experiment 2 and 3, so that is 2 and 3, so square bracket P, this one 2 and 3, the square bracket P is kept constant, whereas that of Q is exactly doubled, that is 0.2 mole to 0.4, during which the rate of reaction increases 4 times, 7.2 into 10 power minus 2 into 4 if I multiply, that would be equal to 2.88 into 10 to the power minus 1, or you can write this 2.88 into 10 power minus 1 as 28.8 into 10 to the power minus 2, and therefore, so the rate increases 4 times. When the concentration of Q is doubled, rate increases 4 times, which shows that order of reaction with respect to Q has to be 2, because 2 to the power 2 is equal to 4. Similarly, if you closely observe the concentration of P and Q from experiment 1 and 4, from experiment 1 and 4, the concentration of Q is kept constant, whereas that of P is increased from 0.1 to 0.4. So that means to say concentration of P is increased 4 times, during which rate also increases by 4 times. Obviously, so when concentration is increased 4 times, rate also increases 4 times, means the rate with respect to P is 1, and therefore the rate law expression becomes rate equals K square bracket P to the power 1 and Q to the power 2, and the correct option becomes option B. Then in the question number 7, the rate constant of a reaction is 0.69 into 10 power minus 2 per minute, and the initial concentration is 0.2 mole per liter. The half-life period. So, and the half-life options which are given are 800 seconds, 600 seconds, 400 seconds, and 6024 seconds. When you look at the unit of rate constant K as per minute, we can come to the conclusion that this is the value of rate constant of a first order reaction. For the first order reaction, T half is equal to 0.693 by K, and obviously 0.693 by 0.69 into the value of rate constant, 0.69 into 10 power minus 2. When you divide that, you get it as 1.004 into 10 to the power 2 minutes. So, and when it is converted into seconds by multiplying with 60, you would get it as 6024 seconds. Obviously, the correct answer becomes option D. And the next question, question number 8, the rate of a first order reaction is 1.8 into 10 to the power minus 3 mole per liter per minute, when the initial concentration of reactant is 0.3 mole per liter. The rate constant in the units of second is. Now, since it is a first order reaction, we can write the rate law expression as rate equals Ka to the power 1, and the rate of reaction is given as 1.8 into 10 power minus 3, and that is equal to K into concentration of reactant is 0.3 mole per liter. Therefore, K is equal to rate divided by concentration, that is 6 into 10 to the power minus 3. So this value is equal to 6 into 10 to the power minus 3, and since the rate constant has to be expressed in seconds, when we divide that by 60, you would get it as 6 by 60, that is 1 by 10 into 10 power minus 3, and that is obviously 10 to the power minus 4 per second, and the correct option becomes answer B. And then in the question number 9, when you plot a graph of log K and 1 by T for the first order reaction, we get a straight line. The slope of this line is given by, you know, the Arrhenius equation is log K equals A log A minus EA by 2.303 RT, and this equation resembles y is equal to C plus mx, and when you plot a graph of what is called log K versus 1 by T, you get a straight line whose slope is equal to minus EA by 2.303 R. So in the equation of straight line y is equal to C plus mx, the value of m is EA minus EA by 2.303 R, and therefore the correct answer becomes option B. And if I move on to the next question, question number 10, for the reaction NO plus O2 arrow mark 2NO2, rate is given as NO2 square into O2. If the volume of reaction vessel is doubled, the rate of reaction, you have been given 4 options, like will diminish to 1/4 or reduce to 1/8, will increase by 4 times, will increase by 8 times. Now when you look at the equation and its rate law equation, rate is equal to KNO2 square into O2. If the volume of the reaction vessel is doubled, like for example, if you have kept 2 moles in a 2 liter container, if the volume of container is enhanced from 2 moles into 2 liters into 4 liters, the concentration becomes half. That means to say 2 mole in 2 liter container, the concentration for that is 1 mole per liter. When this same 2 moles is kept in a 4 liter container, 2 by 4 becomes half, 0.5 mole per liter. So therefore, when the volume of reaction vessel is doubled, concentration becomes half, and therefore rate after what is called doubling the volume is equal to K into NO2 by 2 square and O2 by 2. And if I divide this equation 2 from equation 1, you get rate 2 by rate 1, that is equal to 1 by 8, that is you get it as 1 by 2 square into 1 by 2, obviously 1 by 4 into 1 by 2, and that is equal to 1 by 8, and rate 2 is equal to 1 by 8 times rate 1, means the correct option becomes option B, which will diminish to 1 by 8 of the initial rate of reaction. Now when we move on to question number 11, for the first order reaction, time required for 99% completion of reaction. You know, for the first order reaction, if I take T90 as the time required for 90% completion and T99 as the time required for 99% completion of reaction. If I substitute for 90% completion of reaction, 2.303 by K log 100, if R0 is taken as 100, or is equal to 100 minus 90, that is equal to 10%. So 100 by 10 becomes log 10. You know, log 10 is 1. Obviously T90 can be written as 2.303 by K. And for 99% completion, 2.303 by K into log of 100 by 100 minus 99. So and obviously the T99 will be equal to 2.303 by K into 100 by 1, that is log 100. Now log 100 is 2. Therefore it is T99 is equal to 2.303 by K into 2. Therefore if I write substitute 2.303 by K as T90, then it becomes T99 is equal to 2 times T90. That means time required for 99% completion of a first order reaction is twice the time required for 90% completion, and obviously the correct answer is option C. Question number 12. Hydrolysis of ester in an alkaline medium. You know, hydrolysis of ester in an alkaline medium, like by the hydrolysis carried out in presence of a base like alkali like NaOH. So the ester on hydrolysis with an alkali gives sodium salt of carboxylic acid and alcohol. For this reaction, the rate equation becomes rate equals K into ester to the power 1 and alkali to the power 1. Therefore, so the order of reaction becomes, so when you add the power 1 plus 1, that is equal to 2. So definitely it is a second order reaction, and since the coefficient of ester is 1 and NaOH is 1, molecularity is also 2. So the correct answer becomes second order reaction with molecularity of 2. Remember, if the hydrolysis of ester is carried out in presence of an acid, then it is called acid hydrolysis of ester. That will be a pseudo first order reaction. Hydrolysis of ester carried out only in presence of an alkali like NaOH or KOH, then only it will be a second order reaction with molecularity of 2. And the question number 13, for a second order reaction, the rate at a particular time is x. If the initial concentration is tripled, the rate will become 3x, 9x square, 9x and then 27x. Since it is given as a second order reaction, the rate law equation becomes rate equals Ka square, and that is equal to x. When the concentration of A is tripled, we write concentration of A as 3 times A, and during which the rate law expression becomes rate 2 is equal to K into 3A square. That can be written as 3 square is 9, and therefore K into 9 into square bracket A, and that is equal to x dash. If I write rate 2 by rate 1 and if I divide the equation 2 by equation 1, I will get it as rate 2 by rate 1, and that is equal to x dash by x, that is equal to K into 9A divided by K into 9A square. It has to be K into 9A square divided by Ka square, and the division gives you the value as, after cancellation you get the value as 9. Obviously the rate becomes 9 times, and 9x or option C becomes the correct answer. Then we will move on to question number 14. So this question has, which one of the following is wrongly matched? As I told you just now, saponification of CS3COO C2H5, that is ethyl acetate. Saponification is also called alkali hydrolysis of ester. So alkali hydrolysis of ester is a second order reaction, and that is correctly matched. Whereas acid hydrolysis of CS3COO CS3, which is called methyl acetate, as I told you just now in the previous question, is an example of pseudo unimolecular reaction, and that is also correctly matched. Decomposition of H2O2 is definitely a first order reaction, whereas in the option D, combination of H2 and Br2 to form HBr is given as zero order reaction, but the rate law expression for the combination of H2 and Br2 to produce HBr goes with rate equals KH2 Br2 to the power half. When you add the powers, order of the reaction is 1 plus half, that is equal to 1.5. Definitely the combination of H2 and Br2 to produce HBr is an example of a fractional order reaction and it is not a zero order reaction, and therefore, so option D is wrongly matched. In the question number 15, for a reaction having the rate law expression rate equals Ka power 3 by 2 into B power minus half, if the concentration of both A and B are increased 4 times, the rate of reaction, they say the given options are 4 times, 16 times, decreases 4 times or remains the same. And the rate equation is given as R1 equals K into A power 3 by 2 and B to the power minus half. When the concentration of both the reactants are increased 4 times, A has to be replaced by 4A, B has to be replaced by 4B, during which the rate is given as R2. R2 obviously will be equal to K into 4A to the power 3 by 2 and 4B to the power minus half. And if the equation 2 is divided from equation 1, you get R2 by R1, you get it as 4 to the power 3 by 2 and 4 to the power minus half. So 3 by 2 is 1 and half minus half, 1 and half minus half becomes 1. Obviously the ratio of rates is equal to R2 by R1 is equal to 4 to the power 1, and therefore, so 4 to the power 1 means the rate of reaction increases 4 times when the concentration is changed by 4 times. Therefore, the correct option becomes answer A. Now, if we move on to the question number 16, for a chemical reaction A or mark B, it is observed that the rate of reaction doubles when the concentration of A is increased 4 times. Normally, when the concentration of reactant is increased 4 times, if the rate do not change, we call it as zero order reaction. If the rate also increases 4 times, we call it as first order reaction. They say here the rate of reaction only doubles when the concentration is increased 4 times. Therefore, so its order lies in between that of 0 and 1. If I write the rate equation, rate equals Ka to the power n, wherein we have to find out the value of n or order of the reaction. So they say rate doubles when the concentration of A is increased 4 times. Therefore, 2 into rate 1 if I write, okay, that is equal to K into 4A to the power n, because you are increasing the concentration 4 times, therefore it has to be 4A. And 2 into rate 1 is Ka to the power n, and that is equal to K into 4 to the power n and A to the power n. When we cancel this K and then A power n, you are left with 4 to the power n is equal to 2. So square root of 4 is 2, or 4 to the power half is equal to 2. Obviously, the order of the reaction becomes 1 by 2. And the correct answer is option C. So in the question number 17, they say a first order reaction is 75% complete after 32 minutes. So when was 50% of the reaction completed? For a first order reaction, you know the time required for 75% completion of a reaction, you know very well, it is equal to twice the time required for 50% completion of reaction, and therefore T half is equal to T half is equal to 32 minutes, which is the time for 75% completion, divided by 2, and that is the answer becomes 16 minutes. The correct option becomes option A. Alternatively, you can work out this problem this way also. If I consider R naught as the initial concentration as 100%, then after 1 T half, 50% of the reaction gets completed and 50% of the reactant will be left unreacted. So after 2 T halves, 50% of the remaining 50%. In total, it is 75% of the reaction gets completed. They say that 75% of the reaction gets over in 2 t-halves. That is 32 minutes is equal to 2 t-halves, and obviously t-half becomes 16 minutes. In the question number 18, the reaction A to B follows first order kinetics. The time taken for 0.8 mole of A to produce 0.6 mole of B is 1 hour. What is the time taken for the conversion of 0.9 mole of A to produce 0.67 mole of B? The options are given as 1 hour, 0.5 hour, 0.25 hour and 2 hours. You know, in the reaction you have got 1 mole of A and 1 mole of B. Coefficient of both reactant and product are one and the same. If 0.6 mole of A gets converted into B, definitely 0.6 mole of B is formed out of this 0.8 mole of A in 1 hour. Out of 0.8 mole, if 0.6 mole of B is produced, percentage completion of reaction becomes 0.6 by 0.8 into 100, that is 3 by 4 into 100, you get it as 75%. Similarly, if the concentration of A is taken as 0.9 mole, in the same 1 hour, if in the same duration, if 0.675 mole of B is produced out of 0.9 mole, 0.675 by 0.9 gives you the percentage completion of the same first order reaction. When you calculate this, this would also turn out to 3 by 4 into 100, that is also equal to 75%. That means to say, whether you start the reaction with 0.8 mole of A or 0.9 mole of A, so in the same 1 hour, 75% of the reaction gets completed. Time taken for 75% of the same reaction will be same, and therefore, so if in the first case if it is 1 hour, in the second case also it will be 1 hour, and the 0.9 mole of A is reduced to 0.675 mole in the same 1 hour. Obviously the correct answer becomes option A. We will move on to the next question. Question number 19. A reaction was carried out at 300 Kelvin and 280 Kelvin. The rate constants were found to be K1 and K2 respectively, and you have been asked to find out the relations between rate constants and K2. The options which are given are K2 equals 4 K1, K2 equals 2 K1, and then K2 equals 0.25 K1 and K2 equals 0.5 K1. From the temperature coefficient concept, for every 10 degrees centigrade rise in temperature, the rate constant becomes double. Therefore, for 20 degrees centigrade rise in temperature, because 280 and 300 Kelvin, the difference is just 20 degrees centigrade or 20 Kelvin rise in temperature, the rate constant will definitely becomes 4 times. If I take the rate constant at what is called 280 Kelvin as K2 and the rate constant at 300 Kelvin as K1, K1 will be definitely equal to 4 K2, and therefore K2 is equal to 1 by 4 K1, or that is equal to 0.25 K1. Alternatively, if I consider rate constant at 280 Kelvin as K2, when you raise the temperature from 280 to 290, that is 10 Kelvin rise in temperature, so the rate constant at 298 Kelvin becomes 2 times the rate constant at 280. When you increase the temperature from 290 to 300, the rate constant at 300 will be 2 times the rate constant at 290, and therefore, so this is 2 K2 into 2 becomes 4 K2, and that will be the value of what is called K1. 4K2 equals K1, and therefore K2 is obviously equal to 1 by 4 K1, or that is equal to 0.25 K1, and the correct answer is option C. Yes. Let us move on to the question number 20. The time taken for 90% of a first order reaction to complete is approximately, the options are 1.1 times that of T half, 2.2 times that of T half, and 3.3 times that of T half, and 4.4 times that of T half. Time required for 90%, T 90% is equal to 2.303 by K log R naught by R. For 90% completion of reaction, if I substitute the value of R naught as 100 and R becomes 100 minus 90, and that is equal to 10. Log 100 by 10 is log 10, that is equal to 1, and therefore T 90% is equal to 2.303 by K. And we all know the expression for T half of a first order reaction is given by 0.693 by K. 0.693 can be written as 2.303 into 0.3010 by K, and if I divide the equation 1 from equation 2, that is T 90% by T half, that is equal to, so 1 divided by 0.3010 you get, because 2.303 by K gets cancelled. 1 by 0.3010 can be written as 10 by 3, and obviously this becomes 3.3, and there definitely T 90% equals 3.3 times T half, and the correct answer becomes option C. And then question number 21. Which of the following is a shape selective catalyst? This is a question from catalysis of surface chemistry. The catalytic reaction, which depends on the pore structure of the catalyst and size of the reactant, is normally called shape selective catalyst. And the well known example for shape selective catalyst is ZSM5, and that is also called zeolite catalyst, and ZSM5 is nothing but zeolite C of molecular porosity 5, and definitely the option C of ZSM5 becomes the correct shape selective catalyst. The question number 22. Match the column 1 with column 2 and select the correct options. In the column 1 we have dialysis. Dialysis is a phenomenon in which the colloidal solution is purified by removing the particles of true solution from those of colloids using a suitable membrane. Definitely the dialysis P matches with the what is called purification process of colloids. Peptization, the Q is peptization. So the peptization is nothing but the phenomenon of conversion of freshly prepared precipitate into a colloid. It is something connected with the formation of colloidal solution, and therefore Q matches with 3. And emulsification definitely matches with cleansing action or cleaning action of soap. And electrophoresis is a phenomenon which is normally what is called the process which is performed to find out the nature of charges on the colloidal particles, and it involves definitely coagulation of charges on the colloidal particles, and it matches with the 2, and hence the correct option becomes option B, which is the correct option for the matching of column 1 with the column 2. We will move on to question number 23. During adsorption process, the options are T delta S is positive, delta H minus T delta S is negative, delta H is positive, T delta S and delta G becomes 0. You know, adsorption is a spontaneous phenomenon which is accompanied by decrease in free energy. All spontaneous processes are accompanied by decrease in free energy. And the spontaneity of a reaction is measured in terms of Gibbs equation, delta G is equal to delta H minus T delta S. During adsorption, because of the orderly arrangement or accumulation of molecules on a surface, entropy definitely decreases, and adsorption is an exothermic phenomenon. Obviously delta H is negative, that is enthalpy also decreases. Adsorption is one such phenomenon during which enthalpy, entropy as well as free energy decreases. Therefore, delta H is negative, delta S is negative, and delta G is also negative, because delta H minus T delta S, if delta S is negative, T delta S becomes positive, but delta H is negative and delta G is equal to negative for what is called adsorption phenomenon, and our correct answer is option B. For question number 24, which kind of the following kinds of catalyst can be explained by the adsorption theory? Normally, the mechanism of heterogeneous catalysis is explained based on the concept of chemical adsorption. Heterogeneous catalysis is that type of catalytic reaction in which you have different physical states for reactants and catalyst. So, because of adsorption on the solid surface, the rate of reaction gets enhanced, and hence the mechanism of heterogeneous catalysis is explained by the concept of chemical adsorption, and option A becomes the correct answer. And we will move on to question number 25. Given below, the catalyst and the corresponding reactions are matched. You have to find out the mismatch in that. So, option A is RHCl-PPl3 thrice. This compound PPH3 stands for triphenyl phosphine, and this is called Wilkinson catalyst, that is used in the hydrogenation of alkenes. The next one, TiCl4 plus Al(C2H5) thrice, that is called Ziegler-Natta catalyst, that is triethyl aluminium and titanium tetrachloride, that is called Ziegler-Natta catalyst, which is used in the polymerization of alkenes. And vanadium pentoxide is not used in the Haber's process, and option D, nickel is definitely used in the hydrogenation of oils. And obviously vanadium pentoxide is not used for Haber's process, for which we use only finely divided iron, and molybdenum promoter are being used. Apart from oxides of potassium or aluminum also can be used as promoter, and vanadium pentoxide is not the one which is used in Haber's process, and option C becomes the mismatch in the options which are given. In the question number 26, butter is an example of which type of colloid? So, butter is a gel. In a colloidal gel, the dispersed phase is a liquid and dispersion medium is a solid. Hence, so the butter is an example of a colloidal type. Butter is an example of a gel in which the liquid is dispersed in solid, and therefore the correct option becomes answer B. And in the question number 27, for the adsorption of a gas on a solid surface, the plot of log of x by m versus log p is a linear with a slope which is equal to, Freundlich adsorption isotherm is given by x by m is equal to kp to the power 1 by n, where x is mass of adsorbate and m is mass of adsorbent, and log of x by m, if I take log for this equation, you get it as log of x by m is equal to log k plus 1 by n log p, and this equation resembles the equation of straight line y is equal to c plus mx, for which the value of m is 1 by n, and therefore the slope of the curve is equal to 1 by n, and the correct option is answer B. And in the question number 28, which of the following statements is correct? So in these options, arsenious sulfide sol is being coagulated with what is called ferric iron Ba2 plus and Na2 plus. From the Hardy rule, higher the valency of active ion, greater is the precipitating action. Since arsenious sulfide sol is a negatively charged colloid, so the coagulating power increases with the charge on the cation, and therefore, so the decreasing order of coagulating power is given by Fe3 plus greater than Ba2 plus more than Na plus, and hence, so the coagulating power of Fe3 plus is more than that of Ba2 plus, whose coagulating power is more than that of Na plus. Among the four options which are given, then the correct statement becomes option D. Fe3 plus coagulates arsenious sulfide more effectively than Ba2 plus, and the correct answer becomes option D. In the question number 29, which of the following properties are characteristic of lyophobic salts? So lyophobic salts are normally what is called coagulated by the electrolytes easily at low temperature. So the lyophobic salts are less stable and they need always a stabilizing agent. So the formation of lyophobic salt is definitely irreversible, and hence among the three statements which are given, so the statement 1 consisting of coagulation by electrolyte at low temperature, and statement 3 needs stabilizing agent, both are correct statements with respect to lyophobic salt, and hence the correct option is answer B. Okay. So and then the question number 30. In the question number 30, you have been given the concept of gold number. Gold sol is a negatively charged colloid which can be coagulated or precipitated by the addition of sodium chloride. Now, since gold sol is less stable, its stability is enhanced by the addition of a protective colloid, and the protective action of a protective colloid is expressed in terms of gold number. If I have to tell you the clear statement of gold number, let us suppose we have 10 ml of standard gold salt solution. If I add 1 ml of 10% NaCl solution to the 10 ml of gold salt, if the stability of gold salt has to be retained, it has to be mixed with specific mass of what is called protective colloid. So the gold number is defined as the number of milligrams of dry protective colloid which has to be added to 10 ml of gold salt, so that it will not undergo coagulation or precipitation when you add 1 ml of 10% NaCl solution. Lower the value of gold number, definitely the protective action is more, and therefore the correct answer, if we look into the option, amount of gold present in the colloid is not correct. Amount of gold required to present the colloid, no. Amount of gold required to break the colloid, no way. These things are what is called explanation for gold number, and therefore the correct option is none of these. And in the question number 31, for a reaction half A R mark 2B, the rate of disappearance of A is related to the rate of appearance of B by the expression. So you have been given 4 different expressions. The reaction is given as half A R mark 2B. If I multiply this equation by 2, it will become 2 into half is 1A R mark 2 into 2, that is 4B. 1A R mark 4B, and if I write the rate equation for this, rate of disappearance of A, that is dA by dt, because coefficient of A is 1, and that is equal to coefficient of B is 4, and therefore dA by dt minus dA by dt is equal to 1 by 4 dB by dt, and the correct option definitely is the option D, okay, in the question number 31. And then the question number 32, the rate law for a reaction between the substance A and B is given as rate is equal to Ka to the power n, B to the power m. On doubling the concentration of A and halving the concentration of B, the ratio of new rate to the earlier rate will be, the options are m plus n, n minus m, 2 power n minus m, and then half to the power m plus n. Before you change the concentration, the rate is given as rate 1 equals Ka to the power n and B to the power m. When the concentration of A is doubled and that of B is halved, the new rate, that is R2, is equal to K into, you are doubling the concentration, therefore it is 2A to the power n, you are halving the concentration of B, therefore it is square bracket B to the power m. And if I divide the second equation with one equation, you get R2 by R1, that is equal to K2 power n, A power n, and then B power m. This 2 to the power m comes to the numerator, therefore it is 2 to the power minus m, and in the denominator you are left with K A power n and B power m. When you cancel K A power n B to the power m, you are left with 2 to the power n and 2 to the power minus m, therefore it is 2 to the power n minus m. The correct answer is option C. And then in the question number 33, the time required for 100% completion of a zero order reaction. For a zero order reaction, the expression for rate constant is given by K equals R naught minus R by T, or T is equal to R naught minus R divided by K, in which R naught represents the initial concentration and R represents the concentration of reactant left over after time t. When the reaction is totally complete, that means to say 100% complete, so the concentration of reactant which is left over R square bracket R becomes 0. Definitely the time required for completion of reaction becomes R naught minus 0 by K, or R naught by K, and the correct option is option C. When we move on to question number 34, the rate of a first order reaction is given as 1.5 into 10 to the power minus 2 mole per liter per minute at 0.5 mole concentration of reactant. The half life or T half of the reaction you have been asked to calculate. The options are 23.1 minute, 8.73 minute, 7.53 minute and 0.383 minute. So the first order reaction has the rate law expression as rate equals K R to the power 1, or K is equal to rate divided by concentration. The rate is 1.5 into 10 power minus 2 and the concentration is given as 0.5. and if you simplify this, you get it as 3 into 10 to the power minus 2 per minute. T half of a first order reaction, you know very well, is given by 0.693 by K, that is 0.693 by 3 into 10 to the power minus 2, and 0.693 by 3 would be 0.231, and if this 10 power minus 2 goes to the numerator, it becomes 10 power plus 2. Obviously 0.231 into 100, that is 23.1 minute, and the correct answer becomes what is called option A. And in the question number 25, the substance undergoes first order decomposition. The substance A undergoes first order decomposition. You have been given two parallel reactions, that is conversion of A to B and conversion of A to C, for which the rate constants are given as K1 and K2 and the values are given. And you have been asked to find out the percentage distribution of B and C. So that means percentage of B and percentage of C formed from the decomposition of A. So the percentage formation of B is given by K1 by K1 plus K2, where K1 represents the rate constant for conversion of A to B and K2 represents the rate constant for conversion of A to C. K1 by K1 plus K2 into 100, if you substitute the values of K1 and K2 here and simplify it, it would be ultimately equal to 1.26 by 1.4 into 100, because so the value of K2 is 10 power minus 5. If it is changed to 10 power minus 4, then this 3.8 becomes 0.38. Obviously 1.26 by 1.64 into 100, get it as 76.83% of B. The remaining 23.1% will be that of C, and therefore the correct answer becomes option D. Now let us move on to the question number 36. If activation energy for a reaction is 0 and the rate constant K is given as 1.72 into 10 power 5 per second at 300 Kelvin, the rate constant at 310 will be. You know, if the energy of activation value is given as 0, the Arrhenius equation says log of K2 by K1 is equal to EA by 2.303 or into T2 minus T1 by T1 T2. If I substitute the value of EA as 0, the right hand side value becomes 0, and obviously log K2 by K1 is equal to 0, and therefore since log 1 is 0, K2 by K1 is equal to 1. That means to say K2 is equal to K1, and that is rate constants will remain same at 300 Kelvin as well as 310 Kelvin, and the correct option then becomes K1 equals K2 is equal to 1.72 into 10 to the power 5, which is the option C. And then in the question number 27, consider an endothermic reaction X or a mark Y with activation energies EB and EF respectively for the backward and forward reactions. So the relation is given as EB less than EF, EB more than EF, EB equals EF, and there is no definite relation between EB and EF. If I draw the curve for an endothermic reaction, if E is taken in the y axis and then reaction progress along the x axis, you get the curve for an endothermic reaction like this, and this is what is called EF, and then this is what is called EB, and this difference is called delta H. So for an endothermic reaction, delta H is equal to positive, and that is equal to, because since it is an endothermic reaction, delta H value has to be positive. Delta H is given as EF minus EB, and if it has to be positive, EF among EF and EB, so the higher value should be or EB should be less than EF, and obviously so the energy of activation of backward reaction should be less than the energy of activation of forward reaction, and therefore so the option A in the given options is the correct answer. In the question number 28, T1/4 can be taken as the time taken for concentration of reactant to drop to 3/4 of its initial value. T1/4, or it can also be taken as time required for 25% completion. After 25% completion, you are left with 75% of the reactant in the reactant state, and definitely T1/4 can be taken as the time required for the concentration of reactant to drop to 3/4 of the initial value. If the rate constant for the first order reaction is K, you have been asked to derive the relation between rate constant and T1/4. The options are 0.01/K, 0.29/K, 0.69/K and 0.75/K. If I take T1/4 as the time required for 25% completion, or the time interval in which 75% of the reactant is still left in the reactant state, then I can substitute the R0 value as 100 and R as 75. So T1/4 becomes 2.303/K log 100/75, 2.303/K into log 4/3. Log 4 is 0.6021 and log 3 is 0.4771, and if you subtract this and multiply, you would get the relation as T1/4 is equal to 0.29 divided by K. Obviously the correct answer becomes option B. And into the question number 29, why do most chemical reaction rates increase rapidly as the temperature rises? So the options are: the fraction of molecule with kinetic energy greater than activation energy increases rapidly with temperature. Option B says the average kinetic energy increases with temperature rise. C says activation energy decreases as the temperature rises. D says more collisions takes place between the particles so that the reaction can occur. From the Arrhenius collision theory, we all know that as the temperature rises, the molecules gain more and more kinetic energy and more number of effective collisions are possible, and that leads to what is called increase in the rate of reaction. And obviously option D becomes the correct answer for question number 29. In the question number 40, you have been given a reaction G plus H aromark products. When concentration of both the reactants G and H is doubled, the rate increases by 8 times. However, when the concentration of G is doubled, keeping the concentration of H fixed, the rate is doubled. The overall order of the reaction is, the options are 0, 1, 2 and then 3. In this problem, if the order of reaction with respect to G is X and if the order of reaction with respect to H is Y, on doubling the concentration of G and H, they say the rate becomes 8 times. Definitely when you double the concentration of G and H, the 2 to the power x, because the order with respect to G is X, into 2 to the power y, the order with respect to H is Y. So since you are doubling the concentration of both G and H simultaneously, 2 to the power x into 2 to the power y will be equal to 8, they say, because the rate of reaction is increasing 8 times. Therefore 2 to the power x plus y is equal to 8 can be written as 2 to the power 3. So 2 to the power x plus y is equal to 2 to the power 3. Obviously x plus y becomes 3, and therefore the overall order of the reaction is, that is x plus y is equal to 3, and therefore the correct answer becomes option D. In the question number 41, you have been given the energies of activation of forward and reverse reactions for A2 plus B2 or among 2AB are given as 180 kilojoules and 200 kilojoules respectively. The presence of a catalyst lowers the activation energy of both forward and reaction by 100 kilojoules per mole. The enthalpy change for the reaction A2 plus B2 or among 2AB in presence of catalyst will be, the options are 20, 280, minus 20 and then 300 kilojoule per mole. You know, the delta H or enthalpy change of a reaction is never affected by a catalyst. In any reaction, if it is a reversible reaction, catalyst lowers the activation energy of both forward and backward reactions to the same extent, and obviously delta H or enthalpy change of the reaction is equal to energy of activation of forward reaction minus energy of activation of backward reaction, and that is given as 180 minus 200, obviously it is equal to minus 20 kilojoule per mole, and therefore the correct answer becomes the option C. In the question number 42, the reaction is given as 2A plus B aromatic products. When the concentration of B alone was doubled, the half-life did not change. When the concentration of A alone was doubled, the rate increases by 2 times, and you have been asked to find out the units of rate constant for this reaction. Since the concentration of B alone was doubled, the half-life did not change. That means to say, when the concentration is doubled and the half-life remains same, T half of the reaction does not depend on the concentration, and that is a characteristic property of what is called a first order reaction. Therefore, the order of reaction with respect to A is 1. Then when the concentration of when the rate equation becomes rate equals K A to the power 1 and B to the power 1, and they say that in the next half of the sentence problem, when the concentration of A alone was doubled, the rate increases by 2 times. Obviously, order with respect to A is also 1, order with respect to B is also 1. So therefore, rate of reaction, which is normally expressed as mole per liter per second, is equal to K into concentration of A into concentration of B, that is mole per liter whole square. And if you cancel mole per liter, you are left with liters per mole per second, because it is a second order reaction. Overall order of the reaction is 1 plus 1, that is equal to 2, and hence the rate constant of this second order reaction will have the units liter per mole per second. We shall move on to question number 43. It says, if 60% of a first order reaction was completed in 60 minutes, 50% of the same reaction would be completed approximately in 45 minutes, 60 minutes, 40 minutes and then 50 minutes are the options. The rate constant of a first order reaction K is given as 2.303 by T log of R naught by R, and R naught for 60% completion, if I write R naught as 100, R is equal to 100 minus 60. Definitely K is equal to 2.303 by 60 into log 100 by 40 or log 10 by 4, that is equal to 2.303 by 60 into log 10 minus log 4. and this is equal to log 10 is 1.0, 2.303 by 60 into 1.0 minus 0.6, that is equal to 2.303 by 60 into 0.4, and definitely the value becomes T half is equal to 0.693 by K. If I substitute the value of K as 2.303 by 60 into 0.4 in this expression, 0.693 is written as 2.303 into 0.3010, and then the 60 goes to the numerator. You have 2.303 into 0.3010 into 60 divided by 2.303 into 0.4. 2.303 gets cancelled, and you have 0.3 by 0.4 into 60, which is nothing but 3/4 of the 60 or 45 minutes. Definitely the correct answer becomes option A. And then in the question number 44, a first order reaction is 50% completed in 69.3 minutes. The time required for 90% completion of reaction. The options are 100 minutes, 230 minutes, 230.3 minutes and 125 minutes. The rate constant of a first order reaction is given by 0.693 by T half. 0.693 by T half is given as 69.3, and that is equal to 0.01. For 90% completion, R naught equals 100 and R becomes 100 minus 90, and that is equal to 10. Definitely T is equal to 2.303 by K, which is 0.01 into log 100 by 10 is log 10, and log 10 is equal to 1. So 2.303 by 0.01, when you shift this decimal point to 230, then the denominator becomes 1, and obviously 2.303 by 0.01 becomes 230.3 minutes, and therefore the correct answer becomes option B. In the question number 45, if the rate constant of a reaction has the value K is equal to 163 into 10 power minus 4 mole to the power minus half and S second to the power minus 1, the order of reaction. As we know, the first order rate constant, if the order of reaction is 1, the rate constant of first order is normally either per second or it can be per minute also. If the order is 2, the rate constant will have the units as liter per mole per second. If it is 0 order reaction, the rate constant will have mole per liter per second. Therefore, the units of the rate constant which is given in the problem doesn't match with either that of 1 or 2 or 0 order reactions. Obviously, the correct answer would be none of these. In the question number 46, in a 0 order reaction, for every 10 degree rise in temperature, the rate is doubled. If the temperature is increased from 10 to 100 degree centigrade, the rate of reaction will become 256 times, 512 times, and then the 64 times, and then 128 times. From the concept of what is called temperature coefficient, for every 10 degree centigrade rise in temperature, the rate doubles. When the temperature is raised from 10 to 100 degree centigrade, the increase in rate is equal to 2 to the power n times, where n is given by difference in temperature, that is 100 minus 10 divided by 10, that is equal to 9. So 2 to the power 9 times is equal to 512 times. The correct answer is option B, which is the correct answer, and as it is marked here, it is not A, it is the option B which is the correct answer, because rate increases by 512 times when the temperature is raised from 10 to 100 degrees centigrade. So, in the question number 47, colloidal solutions are not purified by. So, the colloidal solution purification is normally done by dialysis. So, the electrodialysis is also a specific type of dialysis in which the solution is subjected to electrolysis, or by the application of electric field, the particles of true solutions are made are attracted towards the electrodes. Therefore, dialysis and electrodialysis are the methods which are normally used for the purification of colloids. Ultrafiltration is also a similar type of phenomenon in which the colloidal solution is purified. Electrophoresis is a phenomenon which is normally used to find out the nature of charges on the colloidal particles by the application of electric field, and therefore electrophoresis technique is not used for the purification of colloids. So, in the question number 48, which of the following is not an emulsifying agent? The options are gum, oils, protein, agar. Usually the substance which is added to stabilize the emulsions, emulsion is actually a colloidal solution in which one liquid is dispersed in another liquid. That means to say, both dispersed phase and dispersion medium are liquids. When you mix two liquids to form the colloidal solution, we need to add an emulsifying agent which reduces the interfacial tension between the two liquids, and that substance which reduces the tension, interfacial tension, are called emulsifying agents. Normally oils are not used as emulsifying agents, and therefore the correct option becomes option B. In the question number 49, which of the following is most effective in coagulating power of for a hydroxide sol? So, if the hydroxide sol is taken as ferric hydroxide sol, normally the metallic hydroxide sols are positively charged. So, a positively charged colloid can be neutralized or coagulated by the addition of anions, and in the process of coagulation, the anion which has got highest charge would be more effective coagulant. Obviously, among all the four options, the anions are Cl minus chloride ion, SO42 minus sulfate ion, FeCl3 which has got Cl minus ion, whereas in the option C you have ferricyanide ion having 3 minus charges, and hence, so the ferricyanide ion would be more effective coagulant for a positively charged ferric hydroxide sol, and therefore the option C becomes the correct option. Moving on to question number 50, Tyndall effect is not observed in smoke, emulsion, sugar solution and gold sol. Tyndall effect, you know, is one of the property of what is called colloids, which is considered as an optical property. It is a phenomenon in which the colloidal particles scatter the light. Scattering of light by the colloidal particles is considered as Tyndall effect, and this kind of effect is found, or it is observed only with the colloidal solutions. Among the four options which are given, smoke definitely consists of colloidal charged carbon particles dispersed in air, it is a colloid. Emulsion is a type of colloid, as I said, which has got dispersed phase and dispersion medium as liquids. Gold sol is also a colloid, but sugar solution is a true solution. It is a homogeneous solution which do not have the colloidal property, and hence option C becomes the correct answer. So I think with this I will wind up this session, and thank you for watching.